Now you can see, right?
Yes.
So it's my great pleasure to introduce our today's speaker, Irinel Chiorescu from Florida State University. He's also at the National High Magnetic Field Laboratory in Tallahassee, USA. I'll start from a short biography. Irinel has received his Bachelor of Science from Alexandru Ioana Cuza University in Iași, in Romania. Afterwards, he performed his PhD thesis on molecular quantum magnets at the Joseph Fourier University in Grenoble. And interestingly, we realized that about the same time I also was there, almost next door, but we didn't meet, or we do not remember this. Then Irinel performed a 3-year postdoctoral research program at the Delft University of Technology, with the results in superconducting quantum computing area, with the continuation in Michigan State University. And these are from papers with his participation, which I didn't find in the internet, but rather took from my computer. Many or all people who work with superconducting qubits at some point saw these papers, key papers in the field. And now Irinel is, for about already some 20 years, he's at the Florida State University in the Department of Physics and also at the National Mag Laboratory. And about his today's interests and results, I hope we will hear now. Irinel, the floor is yours.
Okay. So I'll share my screen. Thank you very much for the introduction. Let's see, I share. Okay, it works. And it's a great pleasure to be present today via Zoom and show you some of the research results that we have and interests. So as you mentioned, I did my PhD in Grenoble. The focus was on molecular spins, quantum spins, molecular magnetism, and I carried a little bit that interest with me while combining it with this superconducting device business. You mentioned, you showed those two, let's say, big results from Delft when I was postdoc. So that's when I started working with superconducting devices. And at the end, I was trying to combine, in a sense, what I did in the postdoc, what I did in my PhD. And I think that I'll hope to have a coherent presentation today. So the title of my presentation, Engineering Quantum Coherence and Controlling Spin Systems. And this was work done with graduate students and a number of collaborators, and I'll explain along the way. Before I dive right into, I wanna mention a few web pages that I'd like you to visit if you have time. So for those of you that can travel, or maybe young fellows that can travel, check out our graduate program. But generally speaking, you can learn more about our department and the research directions that are done in our university. If you have time to look over those pages, this is the physics department. College of Engineering has a materials science program. We have now a brand new department of material science. And maybe some of you heard of a quantum initiative that we have nowadays at FSU. It's a more recent. It's a rich university, a lot of traditions. You can see here on this side of the screen a student that is role-playing, the role that was played by a chief of a Seminole Nation tribe, and it's planting a spear before each football game. So a lot of tradition, all directions, a great place to live and work. Now, the outline of my presentation, I'll start with a few broad discussion about quantum detection of spin signals, spin qubits, quantum memories, how we face an important challenge, the decoherence of a qubit, then Floquet engineering. I'll discuss about spin photon strong coupling, and I have a few other things. I mean, we'll see how this goes and how long it will take me. And I think it's important, I insist if you can interrupt me at any time, during the presentation. If I'm going too fast or some things are not clear, I could insist a little bit more. So quantum detection of spins, there are a number of methods. I'll not discuss all of them, but let's say the first one I put here, use of an on-chip superconducting cavity that can concentrate photon energy on a small number of quantum spins. And sorry, they concentrate photons energy on a small number of quantum spins, and this increases the spin photon coupling. Okay, so you take the electromagnetic energy in a cavity, you concentrate it in a tiny volume, you have more coupling between the spins that you want to measure and the photon field. We can also use superconducting quantum interference devices, QUID, and then next to them to place samples. Now, it's also possible to use superconducting qubits as spin detector because they have a lot of sensitivity. So it's a good method as well. Artificial atoms, like quantum dots, and the actual atoms transporting junctions. So I want to show you some examples of, if I can go to the next slide. Some photos, references, some techniques on the first row here. For instance, this one right here, done in Grenoble quantum transport through molecular junctions. So you can see the orientation of a spin reflected in the value of the current. Quantum dots on this side. Then a number of systems that can be studied, like nitrogen vacancies in diamonds. So those are, like we can say, those are type of impurities. So very diluted spin impurities in a crystal. So therefore, you can, if by measuring an ensemble, you can see the quantum physics of one spin because they are so far away they don't interact. This one, NV centers, silicon donors. I'll show some measurements that we did with gadolinium. What else? There is also manganese in MgO. Now, this is more along the lines of molecular magnetism. What I have this example here, vanadium 15 molecule. There is also iron 8, manganese 12, where you have one molecule that behaves due to the close interaction, strong interaction inside the molecule, behaves like a single spin with a certain anisotropy that the chemist can build and basically do. I mean, there are a lot of possibilities that chemists can do with this system. So you create one molecule, and then this molecule is replicated in the nodes of a crystal. So now you can have a crystal full of such molecules and the relatively large distance. So the interactions are not that great, not big. So we try to work with, generally speaking, spins that do not interact with each other. So, it's not always easy because dipole interaction, as you know, is long range type of interaction. But we try to minimize the interaction as much as possible because then when you measure an ensemble of such spins, you can get conclusion about the quantum mechanics, the physics of one spin. And it's like the sample is like amplifying the quantum physics of one spin. So now I'm kind of I'll go straight into an important chapter now of my presentation. So, which is a method, I'm going to describe a method we try to use to increase the coherence time. Let's see, I hope I'm not going to be going too fast here. When you have a spin qubit, you can apply a microwave field and make a rotation of that qubit. And this is typically done with old qubits, superconducting qubits, spin qubits, no matter, atoms in traps, and so forth. So then you look at this rotation between spin up and spin down position, and while you are driving, this process of actively driving the qubit between up and down position is called the Rabi oscillation. And scientists always want to increase this with T Rabi, the decay time of this oscillation. And it's not an easy job. This Rabi decay time goes down as the interaction with the outside world increases. Or, as I mentioned before, the interaction with other qubits, right? So we want to keep them as isolated as possible. So when we control the rotation of the qubit, we don't have to deal with any type of interaction, ideally. But of course, in real world, there are always interactions. You cannot get rid of that. And there are two types of processes that will decrease the Rabi time. Pure decoherence, which is a mixture of phase, so the qubit is losing phase, and energy relaxation. This one is called T1 time. And it will be nice if we could always have the Rabi time, at least energy relaxation time. Because the decoherence time, as I mentioned here, is the most important characteristic of a qubit. And you can, so first of all, what the qubit does when it's rotating is losing the phase information, and then it's going to relax to the ground state. So if you can push the coherence to be controlled only by energy relaxation, this is already a nice gain. And then you have to worry, how do you control the energy relaxation part? And to deal with the decoherence time, it is widely used nowadays. This technique of operating the qubit, what is called the sweet spot, sweet point. Sometimes the term of clock transition is used, and it represents the following energy diagram. So what I have here on this lower side part of the slide, energy plotted as a function of magnetic field, and we have. In this case, it's a very simple example, a two-level system. Okay, so you have a 2x2 Hamiltonian. You have one element that is non-diagonal, delta, creates a level repulsion. Without this coupling between states, we would have these dashed lines here, which are across, perfect crossing there. But once you have an off-diagonal term, you have a level repulsion. So it's all very basic, a simple example. We can call the bottom, the ground state 0, the upper state 1, and that will represent 0, 1 states of the qubit. And this is represented here in what is called the laboratory frame. All right, so what you observe when you do the physics with this qubit and you are in laboratory frame, the energy levels, right? Exactly the energy levels of the system, they have a level repulsion. And it's very useful to operate the qubit right here, where the derivative of the energy versus field is 0. That's what is called a saddle point, sweet spot, and as I mentioned, clock transition, different names. And the reason is the following: if you have noise in magnetic field, so imagine you have some perturbation, some oscillations here in the magnetic field, there is no change in the energy here because the first derivative is 0. But it's limited. This technique is limited. You have to find these sweet spots if they exist, or you have to engineer them, try to make them, and then you have to be careful to operate only there. You can have variation from qubit to qubit about the location of this sweet spots. And what we did in a recent work is to introduce a universal method that creates these sweet spots dynamically. So you have your system the way it is, but then for a number of, let's say, microseconds while you operate, we can create such sweet spots and then operate the qubit during those sweet spots, during the existence of these sweet spots. So what is the difference between the two methods? This is a fixed laboratory frame, what I'm plotting here on the left side. And on the right side, what I call dynamical sweet spot, we create on demand. they are creating in the rotating frame. Okay, so I'll give a few more details in a moment about this rotating frame, but the figures look extremely similar, as you can notice. The difference is that instead of having energy, we have quasi-energies that are calculating in the rotating frame. Rotating frame is that I'm rotating with the microwave field, the frequency of the microwave field. So instead of looking at the qubit in the laboratory frame, I'm rotating the same frequency of the microwave, and a number of those things will look static. It's a great way to get rid of time dependence in some situations, get rid of time dependence on the Schrodinger equation. So quasi-energy instead of energies, and then here instead of magnetic field is some parameter of the Hamiltonian. And the rest is basically the same. Now we have this again in examples two-level system, the ground state 0, the excited state 1. The difference is that the level splitting is the actual rotation, the actual frequency of the rotation of the qubit, Rabi frequency. Okay, so let's see. I'm going to dive right now first in some Hamiltonians, and then we're going to show you experimental results. Or actually, before that, I have a nice simulation of what I'm going to talk about. Let's see, what the idea is the following. This green ball here is a qubit, and we provide the shield. And the condition that and you see there is a noisy C underneath in this representation. Let's see how I turn this on. And I don't know how to make it run. I don't know what I'm doing wrong here. Wait, just started. Let's press next. Okay. So the qubit rotates. This is the green ball. And the shield rotates as well. Doesn't have to be at the same position as the qubit. They just have to match from time to time. So the frequencies of the shield and the qubit, they have to be commensurate. And this noisy C underneath all those waves, they come down right under the qubit. Okay, so that's a representation, an illustration of the method. We have a little shield and that protects the qubit by rotating with commensurate frequency. Now let's see the Hamiltonian. Now the fun begins. In laboratory frame, these first two terms here represent the typical Hamiltonian for spin that is driven by a microwave field. Okay, think of all this magnetic resonance technique, ESR, EPR, NMR, MRI, they all use the same part of the Hamiltonian, these first two terms. So F0 as Z this is the Zeeman term. F0 is the frequency, basically the Zeeman splitting, and instead of expressing it as a field, I'm expressing it as a frequency, the same, let's say, energy units, more or less. Here we work usually in hertz. Then the microwave drive has an amplitude of HD. So this is like the power, the microwave field, electromagnetic field intensity. It's coupled with SX operator. And of course, has an oscillation. The microwave field is an electromagnetic field, and it's expressed here as a sine, the frequency of the microwave field, and the time. Now, on top of this traditional Hamiltonian, we also add this piece right here. So this is like a small perturbation. We call it image drive for some technical let's say reasons, some details how we create it. It's an image of another frequency. Maybe I'll not go into the technical details, but anyway, we call it HI. This is a perturbation and is also coupled with SX. The difference is that is at a different frequency. So first you may say, why do we want to do that? Because we complicate our life if you want to treat this Hamiltonian. If you have only the first two terms, you can go in the rotating frame, a frame that rotates with omega plus, and you got rid of time dependence, right? That's the idea of a rotating frame. If I add a third term with a different frequency, well, I'm introducing time dependence back into my problem. And that's exactly what we do. And again, I have these two pictures here at the bottom. The left side is the previous graph. The left side is laboratory frame. The right side is the rotating frame. And I'll describe what happens using these pictures. So F0 is the Zeeman field, and I'm showing it here, this energy splitting between two energy levels. The rapid drive, so the powerful, let's say, microwave that drives the qubit is at omega plus. So in our example here, it's a frequency that is a little bit higher than F0, so we're not at resonance. As you can see, it's F0 plus delta, delta being detuning. So I'm showing here a virtual level as a dashed line. Delta, then F0 minus delta is the frequency of the third term, omega minus. F minus is the perturbation. And there is a difference, therefore, between these two microwave fields, a difference of 2 delta. And the condition that we need, and I'm going to come back to this condition, is that 2 delta is the Rabi frequency divided by some integer, whatever. Okay, k is 1, 2, 3, 4, and it's an integer. So Rabi frequency and delta, they have to be commensurate. In the rotating frame, I can get rid of time dependence on this term as x. We rotate with the microwave frequency, so omega plus. Since I rotate with omega plus, this term disappears. Here we obtain minus delta, which is the detuning part. And in rotating frame, if I would have only these two terms, the fields will be static now. So you have a detuning delta, what I'm showing here in this arrow, vertical field delta, and horizontal static field HD. When you have two fields, you compose them, and this would be the precession axis of the qubit. The total field will be somewhere like this, so composition of two vectors, and the qubit would rotate around it. But we introduce this new term, which is time dependent. So now in this rotating frame, we have an HI field which rotates in this circle here in blue. So rotates with a frequency 2 delta. I did not mention, but it's part of the problem, and it's an important part, this phase is here. See, one is plus 5, minus 5. There is an additional phase, which is kind of mostly due to some imperfection in the constructions of the apparatus. So they do not change any of the discussion in terms of how this thing helps in preserving the Rabi drive, but change the dynamics a lot. So there are situations when the picture is quite simple. What I'm showing here is the case with 0 phases, the 0 additional phases. Or it can be, the dynamics can be very complex. More the dynamics, it gets quite complicated, but in both situations, the coherence is preserved. You have a simple qubit motion or a complex qubit motion, depending on these phases. So if it is a simple qubit motion, phi equals 0, the spin, originally spin up, will rotate like this, and then goes from one orientation to the opposite side. Okay, so rotate and then flips, like spin up, spin down, but around this precession axis. And what we observed is that having this rotating microwave field here, HI, helps a lot with preserving this motion. Instead of decaying quickly, the motion can go on for a long time. And this is really an experimental fact, okay? And well, I'll discuss two explanations. Let's see, what do I have next? A second, next. Okay.
Irinel, before you
Yes.
proceed, let me ask you a question. It seems that Andrei also wants.
Yeah.
Would you please return to the previous slide? Is it similar, the formulation, to the pump probe technique, where you have one resonant strong signal and another one weaker?
So there are similarities. However, I mean, I'm not a specialist in Palm Pro, but I want to mention that the difference between these two fields, you see, I mean, there is a difference that is related to the oscillation frequency. So I don't know, is that the case also in Palm Probe? Is not the sum of energy matches the particular energy. The difference is this Rabi frequency. And I mean, yes, there are similarities. I'm sure, but it's yeah. I think the main aspect is that this is a small. I mean, HI can be really small. This field, HI.
Also, can we see, can we look at the first signal as addressing one? Can we
Yes.
not introduce the dressed state picture for the qubit plus drive?
Yes, the first signal is indeed does addressing, and we can. I mean, we also did a little bit of exploring, using the second quantization, and things can be written in that form as well. And I mean, the point here is that we don't have, I mean, the second signal, F minus, the perturbation. If it is too strong, will, strongly perturb the dynamics. So it will change all the gate operation, like how long does it take, for a pi pulse, for a pi over 2 pulse, and so forth. So here we just want to have it a perturbation that doesn't change much, or almost not at all, the qubit timing. It just makes it longer. The decoherence is not so important anymore. That's in a sense the main idea. So yeah, should I continue?
Andrei, please, you wanted to ask something?
Yeah, maybe just one question about decay. In this picture, in how this trajectory would modify if there is a strong decay process.
Well, so for instance, you see, it's the length of this vector. So it starts with a full length of 1, and then starts rotating around this precession axis. And by the time it ends up on the other side, this blue circle, which is at the end, this blue circle could be tiny, around somewhere here. And that means the length of the vector shrinks. And also, so there are two things. Well, the two things that happen. Instead of having a well-defined vector, is actually like a fan. It spreads out, so will be more of a disk, like a field disk, and then also shorter in length. The relaxation dictates the length of the vector, and if it is a cone instead of a line, of a vector, that's dictated by decoherence. And so yeah, this would be, let's say, a disk somewhere here and closer to the origin.
Okay, thank you.
So okay, next I'm going to show how we can deal with such a time-dependent Hamiltonian. And the important aspect is that this Hamiltonian is periodic. So you can see here a term E minus I omega. So that's the good news. It's periodic. So therefore, we can use the Floquet formalism that it's the idea is that if you have a periodic Hamiltonian, you can take snapshots with a period t, or here 1 over f. This is a period. And instead of dealing with a periodic Hamiltonian, you replace it with an infinite matrix. And this is the idea here shown in this matrix. H0 is a 0 term, what is constant. And I'm showing it here. This is the main drive. Remember, like in typical ESR, EPR, as I mentioned, NMR, where you don't have this additional term. Well, this is a static term. And with the static term, I mean, in rotating frame static term, you can build the diagonal like that. And then we also have, in our case here, subdiagonals, H1 and H minus 1. We do not have H2 and so forth. So for that, you integrate, like as shown, is given by this formula, and over a period, so we have this term now. Okay, so Fouquet formalism allows you to do some analysis of a time dependent of a periodic Hamiltonian by using this infinite matrix. And we observe here, we see the color. This is the main drive. This is a 2x2 Hamiltonian repeating itself like that. And we have blocks, and the small perturbation connects the blocks. So that's the most important message. We obtain this off-diagonal term in rotating frame. And if you remember what I was mentioning a few slides ago about off-diagonal terms, you can create this level repulsion. And now we can create this level repulsion in the rotating frame by using this off-diagonal term. So these blocks, they can be diagonalized. So in the absence of an HI, in the absence of this perturbation, this would be like half of Rabi minus half of Rabi for the first block. And then and so forth, they go down in frequency, in energy. And but now we have this splitting here. And the energy, the quasi-energies look like this. And this is what I'm calling dynamical sweet spot engineering. And we're not the only one doing this at the same time. I noticed when we published this paper was also work done in superconducting qubits by people at in the industry, actually. So this is a method that was used by other groups as well. You can see here quasi-energy plotted as a function. What I have here is the drive divided by delta by the tuning. So those are all dynamical parameters in the Hamiltonian. It's not a static field like a coil, that superconducting coil that controls the field. That's the intensity of the microwave pulse, the tuning of the microwave pulse. And now we can create this level repulsion, meaning that if there is noise in the microwave power, if there is noise in the tuning, which combines both static magnetic field, frequency of the microwave, they're all combined in this delta. If there is noise in any of these parameters, is not seen in first order. And this has powerful implication. So now let me show you some experimental results. So this is really the very important picture for this method, and it's qualitatively showing you how we can split this, create level repulsion in the rotating frame. I'll come back later on in a moment, trying to go deeper into cause-effect relationship, like what actually, why the coherence is better. I mean, the coherence time is better when we operate at this spot. Now, technical implementation, we discuss in more details here in this paper. Simply put, we combine the drive frequency F0 with a low frequency component, and then this is a mixer. And then when you combine these two oscillations, you get plus and sum. The drive is F0 plus delta, and the image is F0 minus delta, and the amplitudes are very different in the procedure that we do. So in this pulse diagram, they are kind of shown with relative similar sizes just to make it visible, but in reality, the image drive, it's a smaller pulse in height. So the results, we apply this method to a number of systems, spin systems, and in red we show what happens without this image pulse, and in blue with this pulse. We have this gadolinium spins with the spin S equals 7/2, like this. And then we see they decay pretty fast. But when we apply this method, the coherence time takes much longer. And the same for spins S equal 5/2, manganese 2+ impurities in MgO crystal. We also use a method for a P1 defect, they are called in diamond. So those are defects that have a spin 1/2. There are two types of defects with spin 1 and spin 1/2 in diamond. And spin 1/2, this is T2, a method that allows to find, let's say, the coherence time of a small package of spins. It's in green here, and you can see when we apply this image pulse, the oscillation lasts for longer. And with our technique, we're limited at 15 microseconds here, but we can reach the T1 time. So see at T1 time, the relaxation envelope is shown here in orange, and the radio oscillations are in blue. I have not discussed it. Let's see if I have a plot. Maybe. Okay, I'll come back. Yes, discuss in a moment. So now we also performed, compared this with simulation. And before the start of my presentation, I mentioned I said a few words about this Qt Python Pro software, let's say package, that allows to simulate quantum objects. It's a very useful package, and that's what we use here. We force the maximum value of the coherence time, T2, to be 2 times T1. This is the maximum we can get in an experiment. It's called, in this situation, the decoherence time is limited only by T1. It's limited only by energy relaxation. So we compare experiment and simulations. And then, so this is what we get. For instance, in this situation, let's say, what do we have here? The first on the left, we look at radio oscillations. So this is the length, the time of the oscillation. And when we don't have any detuning, as you can see on this plot, this alternance between blue and red, and that's spin up, spin down, spin up, spin down. And decays relatively fast, like 0.4 microseconds. In 0.4 microsecond, you can see how these colors are fading. However, when we reach this condition, radio oscillation equal with 2 times delta, you can see that this oscillation lasts for much longer. You can see this oscillation blue-red, going all the way up to microseconds and above that. Then we can do Fourier transform of such an oscillation, right? And when we do Fourier transform as a function of detuning, we see the signal that is, relatively weak and broad, right? When an oscillation decays fast, the Fourier spectrum widens up, so it's broad and not very sharp. But right here at this point, FR equal to delta, we can see in the Fourier transform a very sharp peak, meaning that the lifetime is long. That gives a sharp Fourier peak. And we simulated this with using Qtip. And we just put in Qtip T2 equal to 1. We force it, and gives a very decent comparison between the simulation and experiment. Now this is the case where we have FR equal to delta, but there are some lines that are a bit harder to see, but also like here there is something here that applies to 4 delta, but experimentally it's harder to see. Now, I mentioned, I said a few words about the phase difference between the drive. Like here, this is the main drive, HD, and the image pulse at plus phi and minus phi. And for simplicity, I think we just discarded this second phase. We said theta is 0 or constant. What matters is the difference between these two phases. And no matter the difference between phases, this method helps with coherence, but the dynamics of the qubit can be far more complicated. When this phi is 0, you get a relative, those are experiments done with manganese spins. Phi equals 0 is shown here in the case phi equals 0 in green, and it's a long-lived oscillation, as I mentioned, around the precession axis. When phi is 45, the dynamics is far more complex. It like moves around. It's exploring more of the spin space, and there are beatings. You can see in the Fourier transform how this looks like in the green case here, phi equals 0. The Fourier transform shows a nice peak at the Rabi frequency, some side peaks, but not so important. Whereas at phi 45, the side peaks are very strong. So they are beatings. And it seems both in experiment and in simulation. This on the right side here, it is this platform. This one is measured for gadolinium. This one was for manganese. The method is universal. The spin doesn't matter much. And Fourier transform of the Rabi oscillations, you can see they are periodic with 90 degrees periodicity, both in experiments and in simulation. And I mean, in a sense, allows is not a bad news. You can control this phase phi between two microwave pulses and choose, you know, what type of dynamics you want for the qubit. 1 second. The protocol is independent of the initial state. Now, numerical simulations. Okay, this is also an important aspect because I showed you this. This level separation, level repulsion that we can create in rotating frame, and qualitatively, you know, explains. I have a zero derivative. There is very little noise when you have zero derivative in first order. However, what is the microscopic origin of this phenomenon? Why does it help to have this additional image pulse? So, with the support of our collaborators, Hans de Red and Dr. Mikkelsen, they collaborate with the Jülich Center in Germany, where they have a supercomputer. They are able to simulate 28 spins together. And I mean, it's a huge Hamiltonian, right? It's 2 to power n. So this is something like 2 to power 28 is impressive. I don't think there are many places in the world where such simulation can be done. And we looked at two situations. One case, which I'm calling non-resonant bath, and the other one resonant bath. So in the first case, non-resonant bath, we assume one central spin, like one qubit, and then 27 spins around, which do not resonate. They are not in resonance with the microwave, but they are coupled with the central qubit. This could be nuclear spins. This could be electronic spins, but of a different species. Like if I'm measuring gadolinium, maybe I have vanadium and manganese spins, which are not going to be in resonance with the microwave, but are still there. They're still in interaction, and they can cause decoherence. So this is one case, non-resonant bath. The other case, resonant bath, you have, in this case, 28 identical spins. They're all in resonance with the microwave, but they also have dipolar interaction in between, which is bad, right? Because when they start to rotate, they create local fields on one another, local fields that rotate, and they create a mess. So we wanted to see, does this method help? And there are some details here about the Hamiltonian, the spin Hamiltonian, the bath, and then there is a coupling part. Lambda is a coupling parameter. And you can see here how the spin bath is coupled with this operators. I is for the, let's say, nuclei, or the bath spin, and S is the qubit spin. And then internal interaction within the bath. And here with the resonant bath, we have this dipolar interaction between similar spins, but in different location. And first, we just do the regular drive of the qubit, no special pulse, no second pulse, just one pulse. And we adjust this interaction inside the bass and with the qubit such that we get a relatively fast Rabi drive of 1 microsecond. Then once we set up the problem like that, we apply the second pulse. And the Rabi decay time increases dramatically. So I don't have here the simulation for sake of saving time, but you can see the simulation of the Rabi oscillation in this paper. What I'll show you on the next slide, the correlations, spin-spin correlation inside the bass. And that was, I would say, the surprising result, gives a little bit of an insight on the macroscopic origin of what's happening here. So again, these two cases, non-resonant and resonant. So in the case of non-resonant bass, we look at the internal correlation, spin-spin correlation inside the bass. If there is no second pulse, this is a red curve, without HI, there are no correlation building. You see some dynamics, very flat, very broad, the decay happens fast. So the qubit, the central qubit, is trying to enforce some dynamics in the bass, but the bass kills the qubit. There is a little bit of like neighboring effect on the bass, but it's very broad and dies out quickly. The moment we apply HI, so this second pulse affects the central qubit, but also helps to the interaction with the bass and creates correlation. So again, this story with 0 and 45 degrees, the dynamics can be easier or more complex. If we just look at the 0-1, the 0 phase, this is the phase difference between the two pulses. You can see spikes here in the spin-spin correlation. And also for 45, there is no central spike there. They're beatings, they're two side peaks. So, and this is the bass, okay? This is the Fourier transform inside the bass. So the bass starts to get in sync with the motion of the central qubit. And that was surprising to see. So the qubit is able to tell the bass to start dancing in the same, let's say, frequency. And then in the case of resonant bass, the results in a sense are more dramatic because all spins are resonant with a microwave. And as I mentioned, the dipolar fields start to be a little bit random and they destroy the phase. You see no image field, there's a very fast decoherence to delta. If it is not applied properly, helps, but not that much. The moment we look at the Floquet resonance, we can see a 4 delta, a colorated bass dynamics to delta. If you have spins that are moving with 2 delta, the product of the frequency will give you a signal at 4 delta. This is just on technicality, but the point is that just look at the vertical scale. The correlation peaks in Fourier space go to 2000, whatever units, and then here was just few units. Okay, the same, we have to increase the zoom, basically make a zoom here to see something like 2, 1, 1, 2, and here is 2000. This numerical simulation give a little bit of an insight about a synchronic motion that happens either if they're all resonant, like this case, the dipolar, or if they're not resonant, the bass starts to dance at the same frequency of the qubit. Okay, you'll tell me if I'm going too long. Now, I'll switch the discussion now. I'm going to show you some experiment. I want to discuss about spin photon coupling in cavities.
It's all right if some 10, 15, even 20 minutes.
Okay, because I have a lot. I'll not even tell you how much I have. So you have to keep track of what I'm talking about here, because at some point I think slow down and then we go to discussions. Now, cavity and spins. So we atomic physics and where atoms can fly through a cavity. Here we can put atoms spins in a cavity, and they'll stay there forever. So you gain from this aspect that instead of having atoms flying, the spin is and that are short-lived in the cavity, you can have qubits that stay there forever. With spins, we have to be careful because when you have a crystal, you always have some interaction. We try to minimize the spin-spin interaction as much as possible, but there's always something there. So that's a disadvantage when you compare with atomic physics, quantum optics, when you have one atom at a time, for instance, or a few atoms flying, and they really do not interact with each other. Now, first on experimental consideration when designing such a cavity. And I want to show you how we deal with vacuum fluctuations and how we define this G. It's a very important factor. This G shows the coupling between the qubit and the photon. The idea is the following: the smaller the mode volume, the larger the vacuum magnetic field. So that's why we want to compress. Instead of working with big cavities, like in EPR or EMR, you can have cylindrical cavities that are that big. If you compress them, then you increase the magnetic field, you increase the electromagnetic energy, and also the vacuum fluctuations. I'll come back to that. So also larger the spin or the resonance frequency, the larger this coupling is. This is like the main conclusion. Now, how do we design this cavity? Feed lines and cavities are designed for 50 ohm. In our experiments, and pretty much everybody dealing in this, with this type of science, they work at 50 ohm. Q factor of the cavity can be defined as this impedance, that zero, divided by R, where R represents losses, right? It's a dissipative resistor. Energy is n plus 1/2 times h bar omega, where n is the number of photons in the cavity. Okay, so it's an oscillator. Then we inject the nominal power at the entrance of the cavity. Power, as you know, is energy divided by time, or energy times a rate. So this kappa here is the decay rate of the photons inside the cavity. They show that you send an amount of power, you have a Q factor here, and if you reach this regime that is called optimal coupling, you don't basically get any signal back, or very little. The entire energy goes inside, and then it's going to die within this time defined by kappa, the decay rate. So as you know, we can write power as current squared times R. Remember, this is R here. Current in the cavity, electromagnetic currents. You have current, you have voltages, and they're going to die in the walls due to basically Joule heating the walls. So instead of R, I can write this: I squared Z0 divided by Q. I square Z0, and instead of Q, I can also write Q is also frequency divided by decay rate. So basically, it's the frequency divided by the line width of the cavity. And power is this energy times K. So at the end of the day, I'm getting back to this type of equation, and now I can cross out the decay rate. I introduce this decay rate in R just to create the, let's say, the story, but at the end, I'm just crossing it out. And I can solve for current as a function of energy. So energy times omega divided by Z0, and then you take square root of that. Okay, now we're going to go to the case n equals 0, which means vacuum fluctuations, vacuum magnetic field. When you don't have any photon, you still have this 1/2 h bar omega living inside the cavity. So I replace E in this equation with 1/2 h bar omega. I'm going to get an omega square. So I can give this expression for the current fluctuations. Also, if I multiply with Z0, I get the voltage fluctuations. So I have electromagnetic field now inside the faculty, inside the cavity. This current fluctuation, voltage fluctuation, they create this electromagnetic field. This is a magnetic component. And this, for instance, can be simulated. There are softwares like COMSOL and other softwares. There's a number of such software that electromagnetic simulators. You give the input power or the input voltage, whatever you want to have. Like in this case here, delta I, delta V, and such simulators will tell you how much field you get inside. Well, if I have field, I can have, this is electromagnetic field, but in the rotating frame, it's static and can create like a Zeeman splitting. And this is the coupling term. So this electromagnetic field will couple with S plus to create a coupling term between the ground and excited state of a qubit, 0 and 1. So we have now an energy here that is the coupling basically between these two terms. And this one is H bar G. So at the end of the day, after all this story, what I'm ending up with a way to evaluate G. And this G is important now if I compare it with its interaction between spins and the photons. And it's typically compared against the decay time of the qubit and the decay time of the photon itself. So let's say a few words about spin-photon coupling. The case of one spin or n spins. If I have one spin, the Hamiltonian is called, wait, something is missing, one second. James Cummings Hamiltonian for one spin. This is the energy of the Hamiltonian dimension, and then you produces this term right here, h bar omega A dagger A. I'm using here the notation A for creation and annihilation operators of the photon, and then the spin operators. This is Zeeman term, and then this is this coupling, James Cummings coupling. What happens is the following. You have, I'm showing here the cavity levels, 0, 1, 2, 3, more photons I have, more levels we have, and the qubit is in the ground state. Or let's say, yeah, the spin qubit in my case. Then I can apply a static magnetic field, create a Zeeman splitting as I'm showing here. And if I have a way to put the qubit in the excited state, I can raise all this ladder as shown here. So the ladder is the same ladder, but is raised up. And if I have it right, meaning the frequency of the photon is the same as the frequency, the energy separation due to Zeeman effect, I can bring in resonance these two levels. They're going to interact due to this G. That's why G is so important. And we create splittings between all these levels. And the splitting is bigger and bigger as we go to higher levels. Now, if instead of one spin, we have N, the Hamiltonian is called Tavis-Cummings Hamiltonian. And we create this macroscopic operator here. S is the sum of all spins. And we can write down this summation over all the time, all the spins as just one big operator, SZ, and then here the coupling with the photon. And it turns out that a huge advantage in the situation is that the coupling, I mean, the energy splitting, what I'm showing here in blue, goes from G to G square root of N. And I'll mention that again. Now, let's say we have one atom and one photon. Those are maybe one of the first experiments that were done with superconducting qubit. I did it with a flux qubit. These two papers that appear back to back in 2004. You have 2 by 2 Hamiltonian matrix. Omega 0 is the Zeeman splitting, and omega is the photon energy. And you can see if the photon is in resonance, then these two terms are the same, because they're going to be plus h bar omega 0. But omega is something that you scan, is the external frequency, and you can scan the the frequency there. Now, there is this coupling G, simple Hamiltonian to diagonalize, and there is a level repulsion. And if you can see this drawing, it's from this paper from a Robert Schoenfeld group. There is a splitting here, and then a splitting here, and they are brought in resonance. And I mean, it's actually this one at the bottom, 2G square root of 2, and introduce a new direction, a new method to do quantum non-demolition measurements called dispersive regime. So if I don't have the cavity in resonance, if it is in resonance, we have this vacuum Rabi splitting. There are two levels here. But if it is not in resonance, this is a very important readout method. I can scan the frequency, and the location of the cavity signal is going to tell me if the qubit inside the cavity is it in 0 or 1 state. So it's a dramatic effect on all the the quantum information science. What happened afterwards? This dispersive regime is widely used now. Because, as I said, you don't interact much with the qubit. You measure the cavity only, and the peak, the location of the peak of the cavity will tell you the state of the qubit. Now, if you have one atoms and photons, again, you have 2 by 2 Hamiltonians, again separated by the diagonal terms, separated by 1 photon. And it's a very simple picture. The only difference now is that when you do the diagonalization, you have a separation between these two levels that is G square root of n, number of photons. Then we look at another effect. What happens now if you have a number of spins? This is this balls here are the number of spins, and first we send 1 photon. So we have not this one lowercase n is the number of photons. Now we have, let's say, uppercase n, number of spins. You said 1 photon is going to couple all the spins cooperatively, and you're going to create 2 levels. If you send 2 photons, you're going to create 3 levels. And the number of level increases with the number of photons. And at some point, you're going to create, if I send exactly the number, if the number of photons equals the number of spins, I can create n+1 levels. If I increase the power, so I'm just turning on the power, the microwave power, so from 1, 2, n, if I have a power that is larger than the number of spins, I cannot create more levels. The spin system can give me n+1 levels, but I will change the levels. So it's still n+1, but this level starts to deform. And I'll show you a little example with a system that can be done analytically. Well, this is a Hamiltonian. It's a detail, basically shows how you write the matrix. For this coupling, you see the G coupling between spins and photons appears on this column and this row. And then by doing a transformation, you get this G increased coupling, G square root of n, uppercase n, when uppercase n is the number of spins. And so then we look, basically what I'm showing you now, sort of a passage between quantum to classical world. In quantum case, when I have, here I take just 3 spins because I can do it analytically. 3 spins, I send 1 photon, 2 photons, or 3 photons. And you can do the diagonalization. For instance, for 3 photons, you get 4 states. And that's it in number of states because I'm reaching n. When lowercase n equal with uppercase n, I'm reaching the maximum amount of states that I can create in the spin system. What happens after, if I keep increasing the microwave power and I go above 3 with the number of photons, I'm deforming the state. And this is this continuous line that I'm showing here. When I increase the power, and at some point, the level separation will be equal between these levels, and that's the classical ESR signals, or NMR, or when you don't talk about second quantization, you have one signal, one response. because the level separation between these levels, they are equidistant. The levels are equidistant. Whereas in the quantum case, the levels are not equidistant. So it's a different story. And okay, what can we do in the practice? We have here, yeah, so this is an experimental setup, what we use in our lab. I'll not go into the details. It's a dilution refrigerator. We have a resonator, in our case, a lambda by 4 resonator. At the end of the resonator, we can put the spins. They're going to be connected. They're going to interact with the microwave. Just very, very low amounts of power. And then we have amplifiers to look at the signal. The first study we did was to look at the gadolinium spin systems. And we look at electronuclear transitions. So the Hamiltonian, the spin Hamiltonian is getting a little bit more complex now because we also put the nuclear spark into the Hamiltonian. And we see some signals, and this is what this orange part here is the signal of the cavity signal, but then shows some kinks, and this is due to the interaction with the spin. I have a formula here. It comes out from input-output formalism in the presence of a spin system. S11 is the reflection, the reflected signal, right? So you have there a Lorentzian shape. However, what is important to note, omega C will be the cavity resonance. The cavity resonance is changed by this coupling with spins. The presence of spins perturbs the cavity and gives it a kink, like what I'm showing in this graph like that. Instead of having a flat line at 0, the cavity resonance goes down and up. And the line width has also is affected by the presence of the spins and looks like this Lorentzian. So when they're in interaction, you have a little bit larger Lorentzian width. So we observed, we did this study, we're glad to see that we have quite a good sensitivity because we look at nuclear interactions between electrons and nuclei, and those have a lower natural abundance in gadolinium. This is the spin Hamiltonian for gadolinium. It has a crystal field. What we liked about this system is that the crystal field is strong enough to create something like 20 gigahertz of level separation. This is a frequency that we like where we want to operate. So we don't need to apply much magnetic field to reach this system, to reach this type of frequencies. We looked at, we applied the transverse field, so perpendicular to the crystal axis. You can see here those straight lines would be if the magnetic field would be parallel to C-axis. We apply a field basically almost perpendicular, and the energy levels are flatter. This is part of this story that I mentioned at the beginning with clock transitions and the sweet spot that you can have in spin system. We created levels that are a bit more flat and what's easy to work with. And what else we are doing? We approximated, there is a way to calculate, I mentioned you can estimate GC, the coupling, by looking at the, doing simulation. What we have here, console simulation. We created an omega loop on our chip, and we look at the spins that are placed close to this omega loop, like inside or nearby omega loop, and we can integrate the amount of field that we have and have an estimation of the coupling, and was in good agreement with what we measured. Then the next step, and this was more important, we wanted to achieve the strong coupling that I kept talking about, with 1 photon, n spins, and so forth. And it's the same physics, except that we have to have a stronger coupling between spins. As you can see here, GC has to be bigger than the decay rate of the spin. This is gamma S, and the decay rate of the photon in the cavity. So if you have an interaction that is stronger than the decay of either spin or photon, well, you give them time to interact. Otherwise, they don't have time to interact. The experiments are showing here. So we scan the frequency as a function of magnetic field. And for instance, this cut right here in orange, we show it in this situation right here, and we can see two separated spins, two separated dips, two separated signals, very large separation. So this shows a very large GC factor. So we are happy to observe that, because now you can apply everything that is, talked about, dispersive measurement, quantum non-demolition measurement. You can use those system as quantum memory. You can send a photon. You can store the information about photon in the spins because they have longer relaxation times, especially at low temperature, and then you can retrieve it later on. So there are a number of applications once you are able to achieve this regime. But something we want to, so this is a bit more, the theory that comes along. I mentioned about the crystal field of the spin. This is the Zeeman field, and then those are the terms that we have to use when you are dealing with the strong coupling. The cavity term, and then this interaction between photons and the spin. And we observed this interaction with these two particular levels. Okay, that's what we worked with. The excitation I'm showing with green arrows. An aspect that was important, and I want to just mention it here, decay model applies better in our case than the Tavis-Cummings. This Tavis-Cummings I've already mentioned a few slides ago. Tavis-Cummings for N spin, or James is James Cummings Hamiltonian for single spin. Now, this one is in a rotating frame. Decay Hamiltonian considers the full Hamiltonian rotating and counter-rotating term. And it's important if you have a strong interaction. It turns out this is what we have in our experiment, a very strong spin-photon interaction, and therefore we need all the terms of this interaction. So we basically did simulation in both situations, trying to simulate. Let's see what I have. Yes, you see this green dashed lines. We're trying to simulate the signal using James Cummings or decay Hamiltonian, and it turns out the decay Hamiltonian work much better. Yes, you can see the simulation work very well. Again, we can estimate GC using electromagnetic simulators. Something very interesting that we noticed, I'm not going into detail, actually this still requires study. If you look at this Hamiltonian parameter, those are found, many years ago. Calcium, tungsten, oxygen 4 is a very well-known system. Gadolinium was studied decades ago. So there's nothing new about the system itself. What we did here was we are showing the strong coupling regime with an on-chip cavity and potential application as spin qubits. Now this B44, this reflects certain symmetries of the Hamiltonian. We found a big difference if we get into the strong coupling regime. In the previous study that I showed a few slides ago, we are not in the strong coupling regime. We did not see that. So in the moment where you bring spins in a cavity and there is a strong coupling, it's like the crystal sort of deforms. I mean, the symmetry is preserved. It's the same B44, but the term becomes significantly bigger, and it's really way bigger than the precision that we have. It's not like an error or something. We did this fit, what I'm showing here with this green line using chi-square method. So we're quite confident in the quality of the fit. So yeah, it's just you don't even need to have a photon. You just bring the crystal in the geometry of the cavity, and due to vacuum fluctuations, the crystal changes, and was quite remarkable to see this, and certainly requires more attention. So I can say Oh, I think I'll not go into the detail, but it's an interesting question, though. I want to mention it, and I'll go quickly over this personal spin photon coupling. As I mentioned here, we do have this type of open cavities, and the electromagnetic field dies out very rapidly when I go away from the surface. Within a few microns, I may lose most of the electromagnetic field. It's almost like it's confined at the surface of the cavity. So since the electromagnetic field changes so fast, the coupling between spins and photon will change very fast. So I should get all kinds, like a first intuition, let's say, I should get all kinds of separations here, almost basically a continuum of spin photon couplings, a continuum of separation between this two states, and yet we see only two. So why? How this happens? The key aspect is that this is a cooperative effect between the entire spins ensemble and the field. And what I'm saying here is that each spin has a different spin photon coupling, but to observe only one level splitting. And I'm looking again at this picture that I was saying for 0 photons, 1 photon, we take the 0 of the energy right here. This is a bit of technicality. Now, assume n spins 1/2 for simplicity, spins 1/2, they are collectively in resonance with 1 photon. I can create this basis vector. This is 1 photon and then 0 photons all the way down. This is a ground state, plus, plus, plus for all spins. Now, the existence of this photon can excite the first spin, can excite the second spin, so first can excite the last spin. So the interaction Hamiltonian is going to be written like that. What I'm showing exactly what I just said, that the photon can excite any of the subsequent spins, but all these couplings are different. Okay, they all have different values. And yet we see only 2 levels. And because we have all this, I'm not going to solve this Hamiltonian. I'm just going to, or fully. I'm taking this piece right here, G1, G2, Gn. It's a vector. And we're going to have n-1 vectors that are perpendicular to this one. And therefore, the eigenvectors, so I don't know them. Okay, I do not know these VK vectors, but I know they have to be written like this: a 0 and then a column VK. And because they are perpendicular to G1, G2, Gn, when I apply this interaction Hamiltonian to this type of a row, I'm going to get 0. I get the scalar product between G1, G2, Gn and this vector VK. And I'm going to get a 0. So remember, 0 is this level right here. So those are the eigenvectors. And it turns out that what are called dark states. They are silent. They do not give any signal. So it's not like they don't exist. We don't measure them. When you try to couple these two states, the eigenvector and the ground state with the photon operator, you just get 0. And that's the key aspect. We have dark states, but they are dark, so we don't measure them. So in a sense, we don't care about them. The photon is not going to interact with them. Now, for the other two eigenvectors, they actually can be solved. It's a system of 2 by 2. It's a Hamiltonian 2 by 2. I can create, again, I put this G1, G2, Gn, but I put some particular number here such that H0, H interaction, X0, and the same for state 1, going to give me a nice 0, and I have a coupling under this form. So therefore, I can write this 2 by 2 Hamiltonians under this form. And look what we have a splitting now that is square root of the sum of squares of all the G factors. Okay, so as I said, when I go away from the surface of the cavities, the G factors go down, but the only thing I care is the sum of squares. This is going to create this average G. G average and then square root of n, where n is the number of spins in this system. And so I think I just wanted to show this to answer the question. Sometime I received this question, like, how is this even working if you have so many spins and they all have different couplings? and works like this by creating this average coupling. What time is it? So let's say I do have, but I don't think I'll have time to go into that. There's some other
Yes,
discussion.
Irinel, we'd better give the audience opportunity to ask questions.
Yes, okay. So just one, well, I don't know where the conclusion slide is. So maybe I'll just stop right here. Because I mean, we did, a number of experiments, and I didn't know how long it would take me to go through each of it, and I just put the slides right here. So yeah, thank you very much. Well, yeah.
Thank you very much, Irinel. Very impressive how you managed to characterize and to control multi-level systems, and this in experiment, not in theory.
Yes.
Thank you. Questions, comments, please. Let me start you by asking on several, in fact, it was you said at the end, at several occasions you describe multi-level system as effective two-level systems, or you take into account only some two relevant energy levels. How you decide when this is possible, and if you describe it as a two-level system, do you take other levels into account?
So, yeah, very good question. The temperature has an important role, and then it's the Hamiltonian. Like, sometimes if you have enough anharmonicity in the spin Hamiltonian between levels, and you apply a photon that couples only two levels, then the dynamic happen mostly there. There will be some leakage, but actually, let's see 1 second. I want to, but most of the time it's kind of localized. Now, if you have an harmonic, I mean, quasi-harmonic, by which I mean the spin Hamiltonian. So we did an experiment, for instance, with manganese, a spin 5/2. So therefore, you have 6 levels. And it turns out with this manganese spins and MgO, you can control, you can tune the anharmonicity. So if we tune the magnetic field such that the 6 levels are perfectly equidistant, well, then you cannot talk about a two-level system at first guess. However, it turns out that I'm trying to show, let's say, yeah, well, I don't have enough fingers, but imagine a quasi-harmonic. It starts to go up and down, and if you don't know that you have an harmonic system, a finite harmonic system, let's say, you would think that it's a two-level system because the system just goes up and down, up and down, up and down between the first and the top, and then goes back. But yeah, strictly speaking, that's not a two-level system. So anharmonicity, you can look and you can follow the leakage and the dynamics to other states. So here, actually, this was my next slide. We tried to look at this strong coupling regime with gadolinium. Gadolinium is 7/2, and we use Q-tip exactly for that, okay? To look how the states are getting mixed between, n one photon, n equal 1. With Q-tip, you can work, do basically dynamics using A dagger and A operators, so second quantization. So it's a very performant package. And, we saw oscillations between 5/2, 7/2, sometimes involves -5/2 and -7/2, but they're not, for instance, involving levels in between. I mean, it depends on the initial state. So in temperature, first of all, temperature is very relevant. So yeah, I think the answer is depends on case to case, and even with one system, one spin system, depends on the initial state, depends on so many things. So a lot of care has to be taken. That's absolutely correct. You cannot just say I neglect the rest of the levels. Depends on each case. So, the transition probability are important as well. Like Fermi-Golden rule. When we are looking at this method to increase the coherence time, and I show that it's universal. It works for manganese, works for gadolinium, and they all have multi-level. And while I'm showing just one radio oscillation, all of those because they're anharmonic, strongly anharmonic, and the photons were really coupling two levels, and there was little leakage. There's still leakage, but there's not so much leakage to the upper levels. I hope I answered the question.
That's true. Yes, Andrei, please.
Yeah, maybe I have a general question, but from point of view of student, maybe even. So looking at your affiliation, high magnetic fields, and looking at the results in particular from gadolinium, I would assume that you do not require high magnetic fields. Still, maybe you have other systems where you really need them, or could you
Yes.
comment on that?
Right. So that was the reason why we liked gadolinium in calcium, tungsten, oxygen 4, because it has internal magnetic field. And let's say, if you see this experimental data, the external magnetic field is very small, right? But we already have splittings of in the range of 18, 20 gigahertz in small fields, because, as I said, the crystal field is strong enough. Now, in other systems that we also measure, I mentioned manganese spins in MgO. Manganese spins are like the exact opposite. They have a little bit of anisotropy, but tiny, very, very small anisotropy. So therefore, to reach, gigahertz Zeeman splittings, you have to go to significant. It's like a spin on half. So you need like let's say for this type of frequency, like I'm showing here, close to 20 gigahertz, I'll probably need 0.6 Tesla or so. And that's where the geometry of the devices is very important. They have to be planar. And apply the magnetic field in plane. You cannot apply magnetic field perpendicular to a superconducting device. Even the smallest angle will destroy the sample. Not the spins, will destroy the resonator or squids. I have not shown, I have some slides here, I have not shown what we did with squids. They are very sensitive devices. Superconductivity and magnetic field, they don't go well, right? The magnetic field will always try to kill superconductivity, and will do it. But that's why we apply the magnetic field in plane. That's one aspect. The second aspect, in the case of studies where we use squids, we cannot use tunnel junctions. So, all these qubits, superconducting qubits, they are using tunnel junctions, and they are fine in small fields. If you go to high field, like I mentioned, let's say 0.6 Tesla or so, what happens is that you have the thickness of the, let's say, I'm showing, let's say, thickness of aluminum qubits, for instance. You have two layers with an oxide barrier in between. If you apply a strong magnetic field like that, you can enclose at some point a fine knot in the cross-section of the junction. And the moment you have a fine knot that is captured in the junction, is done, is dead. So a tunnel junction, I would say, is too thick to be operated in high fields. So what we do then, we use what is called constrictions. So our squids, if you have a niobium line, I'm showing here, let's say, a line of 50 micrometers, then, sorry, as I said, like let's say 200 nanometer, and then in the middle you shrink to the smallest possible that you can, like few tenths of nanometers, and then it's open again. So when you create a constriction like that, it's similar from some point of view to a tunnel junction, in the sense that you're going to have an inductance, kinetic inductance that is higher and creates the Josephson effect. It looks different in the modulation curve and such. I mean, there's significant differences, but it will still be a very good flux detector. So, and it can be thin. We use niobium, a few nanometer thickness in fields up to 7 Tesla, and behave just fine. You cannot do that if you have a tunnel junction. you get close to, I don't know, maybe half Tesla or so, and you're gonna destroy the junction. I mean, not destroy the junction, but the superconductivity, yeah, the Josephson effect. So yeah, those are important aspects that we have to take into account when we deal with high fields. Yeah.
Thank you. Very interesting.
Many thanks, Irinel. It was particularly interesting to hear that you are using squids based on constrictions. Maybe me and
Yeah,
colleagues.
that will be another talk. I mean, I have them here, but we'll spend another hour or so. So yeah, this for some other opportunity.
Yeah. Probably at this point, on behalf of the audience, I will express our gratitude for the nice lecture, for presenting your cutting-edge, very interesting, impressive results.
Okay.
Thanks.
Yes. Thank you very much.
Thank you.
It was a pleasure to meet you.
Good, and we'll stay in touch. You know, I hope
Yes.
yeah, if I can answer other question or some other opportunity then. Okay.
We will.
So I'll leave the Zoom then.
Yes. Bye-bye.
Thank
Yes.
you.
Bye bye.
Bye.
Mm.
Bye bye.